Hey guys, welcome to this session by Intellipaat. So in this session, we're going to look into statistics interview questions. Statistics is really important and one of the foundation of data science. So in this session, we're going to look into interview questions of statistics from the very basic to the most advanced questions so that it will help you clear an interview. And before moving on with this session, please subscribe to our channel so that you don't miss our upcoming videos, and also leave a like if you enjoy our content. Now, without any further ado, let's begin with this session.
Hey guys, welcome to this session on Statistics Interview Questions by Intellipaat. Statistics is by far one of the most important concepts in data science, machine learning in general. So it's an important concept, and when you're going for an interview as a data scientist or a machine learning engineer, you are expected to know a lot about statistics. So in this video, we'll take a look at some of the interview questions and their answers and try and understand what kind of questions come most predominantly in a data science or machine learning engineering interview. And these are the kinds of questions that you get related to statistics. So let's take a look at these questions one by one. Before we begin, we'd like to ask you to subscribe to our channel and click on the notification bell icon so that you never miss another update. If you like this video, click on the like button, and in the comment section down below, let us know what else you would like for us to cover next. So let's take a look at these. The first question is, what is the difference between inferential statistics and descriptive statistics? So there are different kinds of statistical measures, the different kinds of ways through which you can perform statistics. These are two of the most popular ones: descriptive statistics and inferential statistics. So to give you an exact and precise definition, descriptive statistics, as the name suggests, provides exact and accurate information, describes the data as a whole. Inferential statistics, which is derived from the word inference, is the kind of statistical measures in which we provide statistical information from sample of data to reach a conclusion about a population. So to give you an example, suppose you want to make certain kinds of assumptions about a group of people. Let's say the group of people are 100 million people, and you want to make sure that all of them are subscribed to a particular ideology. Maybe they have certain agendas, many kinds of things. So in case you wish to do that, instead of asking all the 1 million people to submit answers to a questionnaire, the better way of doing it would be to get a small subset of these people, that's called the sample, out of all the 100 million people, which is called the population. And from there on, you perform statistical measures in order to draw certain conclusions. Once those conclusions are drawn for that particular group of people, the sample, after gaining that kind of understanding, then what you can do is you can sort of think of it as being applied to the entire population. So that's the way inferential and descriptive statistics work. So what is the difference between population and sample inferential statistics? So as we have already seen, population is the larger context and sample is the smaller context. But to broaden it out a little bit, from the population, we take the sample. Now think of it as an entire body of work and then some piece of work from there. So we cannot work on the population either due to computational cost or due to the availability of data points for the population. Another way of thinking about it would be to think about it in the way that you have some data, you have a large number of data about a lot of people, but you can't use all of it because it's a huge number of data. That's not really possible for you to compute the entire piece of data. But what you can do is you can randomly select a little subset of that data and draw conclusion from that. So this is what's called statistical measuring in inferential statistics. And from here we take the sample. Sample is the small subset that we chose, and population is the larger subset from which we choose the sample. There are different ways of choosing the sample. We have to be very careful when we're choosing a sample data from a population, because we don't want to take wrong samples or take samples in a way that causes certain kind of biases. We'll cover those in future questions, but we don't want to make mistakes in this step, because this is the step that forms the foundation of everything that we're going to be doing as we move forward. So from the sample statistic, we calculate the statistic. Now, after that, getting the sample data from the population data, we perform the inferential statistical methods, and with that, from the sample statistics, we conclude about the population. So this small group of data set that we use in order to draw conclusion about a larger data set. All right, let's take a look at what is quantitative and qualitative data. So these are two kinds of data sets that you might have to deal with: quantitative and qualitative. It's quite easy to understand what these mean if you take a look at the etymology of the words. In quantitative data, it deals with quantity, so it's known as numeric data. If you're ever dealing with numbers, age, number of people that subscribe to a particular channel, number of people around a particular age, any kind of quantity, the number of people who bought a particular phone, the amount of phone that was sold over a period of time, the amount of product that was sold over a year. These kinds of things, they are quantitative data that tell you about the quantity of something that you wish to know. Qualitative data, on the other hand, is also called categorical data. This is data that is not numeric in nature. So this is someone's name, identity, gender. You can also think of it as the age group, like a toddler, a teenager. These are not numeric values because a teenager could be anyone, either 12 years old, 13 years old, 14 years old. They are all teenagers. Whether they are old or whether they are young, these are the kinds of things that are known as qualitative data. They tell you about quality of a person or quality of a data point. So this is what the difference between quantitative and qualitative data is. Then comes the 5-number summary. This is by far one of the most important concepts and one of the most asked questions in statistics to sort of gauge your understanding of how much you know about statistics. This is also one of the most basic things that you should absolutely know. So the 5-number summary is a summary of data extracted usually in descriptive statistics. So when you're trying to describe the entire data set, you get some data and you create a 5-number summary of that data. This summary usually contains information such as low extreme, which is the minimum. So if I give you a bunch of numbers and I ask you, okay, tell me the number that is of the minimum value in this collection of numbers. That's the first thing if you are trying to create a 5-number summary. Then there's the lower quartile, which is Q1, which is the 25th percentile if you would like to call that. Then there's median, which is the 50th percentile. Then there's upper quartile, which is Q3, which is 75th percentile. And then there is upper extreme, which is the maximum value. Now, of course, 5-number summary is not the only summary that you can draw. You can add more things into it, such as the mean, the standard deviation, and all other kinds of things. But to get started, this is the best way to sort of give you a summary of the data that you have. What is the range of the data, that is from minimum to maximum? How is the data spread out? What is the data point right at the middle, which is median? What is the data point at the 25th percentile, which is the data point that is between the minimum value and the median value? Similarly, Q3 is the value that is right at the middle of median and the upper extreme or the maximum value. So that's how you can sort of show the distribution of the data and how the values interchange and how the values are spread over the entire number line. So what is the benefit of a box plot? So box plot is by far one of the most misunderstood concepts in statistics. Box plots are used predominantly when we're trying to give you a visual representation or graphical representation of the 5-number summary. And it also can be used to compare groups of histograms. Since histograms are just quantitative data, we can generate a 5-number summary from that histogram, and then we can create a box plot out of it. Other plots such as pie charts and scatter plots and all of that, they are quite easily understood because they're very intuitive. You take a look at that, you take a look at pie chart, you figure out, okay, this is the percentage of a share from 100% of a value. So that's how you can understand that. Scatter plot tells you the relationship between two values and many other kinds of things. Do the value cluster up against each other? Do the values spread out over the entire sheet? How does that work? So that's the way these things work. But box plot is a little misunderstood because it's not very intuitive. When you take a look at a box plot, it doesn't make much sense. So if someone asks you, and this is why the statistical interview questions ask about box plot, because as 5-number summaries are really important, and it's important for you to be able to visually understand what a 5-number summary represents. You draw a box plot so that it can be shared with different people, and you can compare and contrast different box plots. So a box plot is basically a graphical representation of the 5-number summary. You get all the data that you have gotten previously in the 5-number summary, but you represent it in a way that's easier for you to comprehend and easier for you to explain to other people. So that's what the 5 box plots are there for you to do. The next question is, what is mean? Now, again, this might seem like a really simple question, but mean is actually one of the things that people find it really difficult to define. Many people define it as simply being a summary of the entire data point, which is very vague and not very useful. If you're trying to learn something, you should make sure you understand what it means, since mean is one of the most basic and one of the most important concepts. This is a question that is asked most frequently. Now the answer to this is quite simple. Mean is the average of a collection of values. Calculation of it is very simple. You just calculate it by dividing the sum of all observations by the number of observations.
Okay guys, if you're looking for an end-to-end training in statistics, Intellipaat provides a complete certification training on statistics for data science, and those details are available in the description box. Now let's continue this session.
So if you have 5 numbers going from 1, 2, 3, 4, 5, you calculate the sum of those numbers, which is 15, and then you divide it by the number of observations, which is 5. 5 divided by 15, you get 3. 3 is the mean of the values. So that's how you create the mean. You understand what the mean is and how you calculate it. Now comes standard deviation. Even though mean is quite misunderstood, standard deviation is a little difficult for people to explain in succinct terms. So if it gives off the representation that you don't know what you're talking about when you're talking about standard deviation. Standard deviation is not that difficult to understand. As the name suggests, it is a magnitude of how far are the data points from the mean, or how much do they deviate from the mean. So if I calculate the mean, so what is the magnitude by which these values deviate from the mean or are spread out around the mean? It gives you an idea of how the spread of the data is going to be if you draw a curve of data. If you were to plot it, how far away does the spread go? That's what standard deviation is. So let's suppose that you have a value set and you get a mean of 5 and the value of minimum and maximum is 0 and 10. So the mean is quite close to the extreme ends of the data, and even if you were to plot it, you would get simple plot and it won't be very spread out. On the other hand, if it was like you get a mean of 15 and you have values of negative 35 and positive 157, then the mean is somewhere around the middle. But the problem is that the data is quite spread out. So that's how the spread of the data is defined. So that's one way to think about it as well. That's what standard deviation is all about. It's a magnitude of how far are the data points from the mean. How far is the data spread out from the mean, to be exact. Then comes symmetric distribution. This is another important concept because it's a little difficult to explain in a simple, succinct manner. When you're in an interview, people are looking for you to describe these basic topics in the best possible way, which is why these questions are asked so often. If you fumble in these topics, then they know that either you have no confidence in what you're talking about, or you don't know what you're trying to tell them. So what does symmetric distribution mean? This is an important question because symmetric distribution is at the heart of many of the statistical techniques that we take a look at. So a symmetric distribution means that the part of the distribution that is on the left-hand side of the median is the same as the part of the distribution on the right-hand side of the median. For example, and there are many examples of symmetric distribution: uniform distribution, binomial distribution, and normal distribution. Symmetric, for those of you who are unaware, is a term that means that if you were to cut something from the middle, create a half portion of it, the left hand side portion will be exactly the same as the right hand side portion. So this is why it's called symmetric distribution, because when we create a distribution plot, as you can see in the image here, it is supposed to look exactly the same from the left hand side portion to the right hand side portion. If I were to fold it over onto itself, it should exactly cover the other side. It should not spill over and it should not leave some space. That's the way that symmetric distribution works. Then comes, what is the relationship between mean and median in a normal distribution? So this is a question to help you understand what is mean and median and what makes a normal distribution stand out. So when you calculate some data of data that is giving you a normal distribution, which is a symmetric distribution, what is the definition or what is the relationship between mean and median of that data? So in a normal distribution, mean is equal to the median. So to again give you an example, if you were to create a plot of data such as 1, 2, 3, 4, 5. So you have 1, 2, 3, 4, and 5. Calculate the mean of the data, you get 5 plus 4 plus 3 plus 2 plus 1, which is basically just 15. Divided by 5, you get 3. Similarly, the median is going to be, since it's all in one line and it's all in ascending order, we get 3 as the median. Since mean is 3 and median is 3, it's a normal distribution. If you were to plot it, you will get a normal distribution as well. Of course, in real world, the data is not so easy to interpret. There's a lot of data, all of it is jumbled up and it's difficult to grasp. You make use of certain computer programs, you can make use of certain statistical measures, But at the end of the day, if you want to figure out whether or not plotting something will give you a normal distribution, just calculate the mean and the median and take a look at the difference between the two. If the difference is not large, then the mean and median will give you normal distribution or almost a normal distribution. But if it is too far off from each other, then it's going to not give you a normal distribution, but it's going to give you distributions that are skewed. And we'll take a look at what a skewed distribution means in a moment. So what is an outlier? Outliers are by far one of the most common problems that we get when we are dealing with data. This is why we get questions like these asked in data science and machine learning engineering interviews. Data science makes heavy use of data sets, and if you don't understand what an outlier is and how it affects your entire process of machine learning or how it affects your entire process of modeling the data to create a predictive model, then you don't really understand how data science works. So before understanding how it affects our models, we have to understand what an outlier is. An outlier is a value in a collection of values that is either much larger or much smaller than other values in the collection. To give an example, let's say that you have 5 values. You have 1, 2, 3, and 4. These are the first 4 values that you get. All of these values are quite compact. They are quite close to each other. There's not a lot of difference between the extreme ends of the 4 values that we have gotten. But let's say that the fifth value that we get is 157. This is quite far off from all the other values. It's not the same as all the values that we have gotten. It's quite far off from what we would like to use. So how do you deal with that? That's called an outlier. Similarly, if it was like negative 251, it is also an outlier. Outliers can lie on either end of the number line. If you put your data on a number line and some data are at the extreme end of the value spectrum, that means that you are facing problems with an outlier. They negatively impact your statistical models. So if you're trying to create a model that can predict the next number, so 1, 2, 3, 4, if that's the data, then the next number is going to be 5. This is quite easy actually, but you can see how easy it is. Now let's say one value is an incorrect value that we get. It's 157. Now our statistical model is entirely confused. It thinks that 80% of the data is conforming to one pattern and 20% of the data is not conforming to that pattern, and it is very difficult for it to make sense of this difference in the magnitude. So to deal with outliers, we'll take a look at how to deal with outliers. But first you need to figure out how can you find out an outlier. An outlier is a difficult thing to understand at first, but how can you find it out? Once you know that you might have some outliers, when you're dealing with data in a large scale, finding out outliers, it can be a bit difficult to do by hand. So you need help of certain formulas. Now, this is where the 5-number summary comes into play. This is why we discussed it in the earlier sections, and this is why it's so important to know what a 5-number summary is and how you can calculate it. So you can use the 5-number summary to identify the outliers. Any values smaller than Q1 subtract by 1.5 times the IQR. These might sound like terms that are not very easy to understand. So Q1 is the first quartile, is the 25th percentile. It is the value. So if you take all the values and find the value that is right in the middle of the entire collection of data, if you put it in ascending order, that's the median. And if you find the value in the middle of the smallest value and the median value, that's the first quartile. That's the 25th percentile. So you get that value, and then you subtract 1.5 multiplied by the interquartile range. This is the value that is interquartile range means the magnitude of the difference between Q1 and Q3. So you get 75th percentile, you get the 25th percentile, and then you subtract them with each other. Whatever value you get, that's the value that you can consider as the interquartile range or the range of the quartiles. Then you multiply it by 1.5, which is basically you are expanding the value a little bit more. You are making it 1.5 times of what it is. You're making it larger than what it is. And then you subtract it from Q1. So you get some value at the end of Q1, and then you sort of expand it a little bit. Any value that's smaller than that is an outlier. It's a data set that it's a data point that should not really be there. It doesn't make sense for the data to be smaller than this number. So that's the number that you can think of. But that's only if the data, an outlier is in the negatives or is smaller than the smallest value. What about the largest number? Now that is where the Q3 comes into play. So you take Q3 and you add 1.5 multiplied by IQR, which is the interquartile range. So on the other hand, the number that are higher than what the maximum value should be, that's the other kind of outlier. And to calculate it, you do this. So if your number is smaller than first quartile subtracted from 1.5 times the interquartile range, and if a number is larger than third quartile plus the 1.5 times interquartile range, then it is considered an outlier.
Okay guys, if you're looking for an end-to-end training in statistics, Intellipaat provides a complete certification training on statistics for data science, and those details are available in the description box below. Now let's continue this session.
So that's how you can create an outlier. To deal with an outlier is quite simple. You remove the outliers without thinking about it, because outliers are really detrimental to our statistical measuring. Outliers exist because of problems in statistical measuring. When we're trying to take the sample, some data sets are just too different from what we expect, some exceptional data points, or it could be issues in the measuring devices that we used. If you're trying to take temperatures, maybe the thermometer was broken and it didn't give the right reading. Maybe it was polluted, something happened and we get the wrong inputs. And these wrong inputs affect our statistical models, because the reality is not based on the outliers, it's based on the collection of data that is quite close to each other. Now let's take a look at what is the relationship between mean and median in a normal distribution. So in a normal distribution, mean is equal to the median. As we have taken a look at symmetrical distribution, normal distribution is just another name. This is a question that is used to throw off people from what they are trying to learn. So if you know that symmetrical distribution is normal distribution, then it's going to be really easy for you to use. But these questions come in quite handy, because when people are studying these things, they learn that, okay, symmetrical distribution, you have mean and median, they are equal to each other. But if you learn the normal distribution, you learn that mean and median are equal to each other. And then you go to an interview and they ask something else. So if you've learned symmetrical distribution and they ask normal distribution, you should not be confused and thrown off the scent. You should understand that these are the same things and they have the same value. So mean is equal to the median. These questions are quite frequent. They try to get a sense of a person's understanding of how much they know about statistical measuring, how much they know about symmetrical distributions, how much they know about distributions that are the same with different names. So that's how this works. So what does the bell curve distribution mean? This is a term that is used quite frequently when we're trying to describe a distribution in our statistical measurings. So what does it actually mean? A bell curve distribution, or a normal distribution as it might also be called, is called a bell curve distribution because of the shape of the distribution that looks like a bell. If you've ever taken a look at a bell at any place, it looks in the shape of a bell curve distribution. If you take a look at the image that is at the top right next to the calculator, you can take a look at it and you can imagine why it's called a bell curve distribution. It is symmetrical. It is looking like a bell, so that's why it's called a bell curve distribution. Bells are also quite symmetrical, so that's one of the reasons why it's called that. So how does standard error and margin of error are related? So what happens to standard error as the margin of error decreases or increases? What is the relationship between the two? So as the standard error increases, the margin of error also increases. This is also known as a positive correlation. So when one value increases, the other value increases as well. Think of it as the relationship between the age and height. As the age of a person increases, their height also tends to increase. However, that relationship isn't carried for a long time. After a certain age, your height stops increasing. But as a good threshold, you can understand that how that works. So that's how the standard error and margin of error are related to each other. And now we come to another question that comes into hypothesis testing. If you've ever worked with statistical analysis and understanding the data, one of the things that we get to understand is, what does the degree of freedom mean? So as the name suggests, degree of freedom is defined as the number of options that we have. So if we want to take a look at a new scheme that a cinema hall has introduced, it has introduced three kinds of popcorns. Three kinds of popcorn buckets or snack buckets: a small bucket, a medium-sized bucket, and a large-sized bucket. And we want to take a look at what do people prefer to choose most of the time in a particular cinema hall. So this is where we get the word degree of freedom. The person who is being studied has three options, three choices: the smallest box, the medium-sized box, and the largest box. So it is used with T distributions and Z distributions. These are the kinds of distributions that we use when you're trying to make sure that the population sample that you have chosen and the conclusion that you have drawn with it is in congruence with the entire population. So you take the entire population and you take the sample statistic and you try to figure out whether or not the conclusion that you drew about that conclusion is in line with the entire population. That tells you the sampling was correct, that there was no error in sampling, and so on. So the degree of freedom basically means that the number of options that you have. Whenever you're trying to create a statistical model, you need to provide it with certain options. An option could be as simple as a binary option in which either a person chooses to buy something or they choose to ignore it. Or it could be a larger, broader spectrum of options. Out of the 10 ice cream flavors that were given, which one did the most people go for and why? What were the genders of the people who went with the one kind of flavor, and what were the gender of people who went with other kind of flavor? So these are the kinds of things that we're talking about. If they were given 10 kinds of ice cream flavors, then they have a degree of freedom of 10. If they were given 3 kinds of boxes of popcorn, then the degree of freedom is 3. And this is what is used to determine whether or not the conclusions that are drawn prove the hypothesis or disprove the hypothesis. So now let's take a look at what is covariance. So covariance is a measure of how two variables change together. Now, if you have ever worked with statistical modeling of data, if two variables have a strong relationship with each other, that means that one variable values in one variable change as the value in another variable change, we're trying to create a model that could have a negative impact. It may also not, but if the relationship is really, really strong, then it could have a negative impact on the kind of model that we're trying to create. So it's important to understand that relationship between different variables. Now in this one, we have what is covariance. Covariance is the measure of how two variables change together. Does the increase in one variable lead to an increase in another variable? Or does it lead to the decrease in another variable? Is the covariance positive, negative, or neutral? Neutral basically means that there is no relationship between two variables. One variable increases has no effect on another variable. So to give you an example of these kinds of relationship, think of it as this. You have some data set that has a person's age and date of birth. As the date of birth increases, the age is also going to increase because these two things are calculated on top of each other. So that's really easy to understand. Then comes the after date of birth, there's for negative correlation we have or for positive correlation, another example could be a person's age and their height. So as the age of a person increases, the height of the person also increases. So one has an effect on another. Then comes neutral covariance. In the neutral covariance relationship, what happens is a change in one variable has no effect on the change of another variable. So a person's you can think of it as a person's choice of food and their income level. That could be a relationship of neutral correlation because there doesn't seem to be much relationship in these two things. Then comes negative correlation, in which increase in one thing leads to decrease in another. So you can think of it as a person's age and their bone density. As the person's age increases, their bone density starts to decrease when they start getting older. So that these are kinds of things that you can take a look at. So that's what covariance does. It tells us whether or not the change in one variable has effect on other variables. Let's take a look at one sample t-test. So in case you're not familiar, one sample t-test is a kind of statistical hypothesis testing. One sample t-test is one of the kind of t-test you can do. You can also do two sample t-tests and other kinds of t-tests as well. So one sample t-test is a statistical hypothesis test used to determine whether an unknown population mean is different from the specific value. So a good idea to understand this is basically if you are trying to create a data, you're trying to draw some statistical inferences from a student's data set. You have data about each specific student and you want to figure out whether or not that particular data about that student is in congruence with all the population data that you have. So you usually use t-tests when you have continuous data. So for instance, you have data about a person's age, that's continuous data, stock prices, when you have stock prices, when you have blood charts, diabetes charts, these kinds of things. So what it allows you to do is it allows you to determine whether an unknown population mean is different from a specific value. So if we have a specific value for a sample data and we want to take a look at the mean of the entire population, does that signify a significant difference that we can measure it as an outlier or something like that? That's what one sample t-test allows us to do. Then comes alternative hypothesis. So alternative hypothesis is also denoted by H1. This basically is a statement that must be true if the null hypothesis is false. Think of it this way. If you have an alternative hypothesis, that means that the statement is true when the null hypothesis is false. So these two things are diametrically opposed to each other. Now, if you think about it, in statistical measuring, we are trying to prove something. That something is written down in a hypothesis.
Okay guys, if you're looking for an end-to-end training in statistics, Intellipaat provides a complete certification training on statistics for data science, and those details are available in the description box below. Now let's continue this session.
So we have two kinds of hypotheses, as we have already discussed: null hypothesis and alternative hypothesis. Null hypothesis is something that is in inferential statistics. The null hypothesis is the default hypothesis that a quality to be measured is zero. To give you another example, let's say that you're trying to draw a conclusion about a group of people in a large population, and the conclusion that null hypothesis will allow you to do is it allows you to prove the negative. It allows you to prove that, okay, we are trying to prove that this group of people is representative of the entire collection of population. But in null hypothesis, you write it in a negative way. You write, okay, this population is not representative of the entire population. On the other hand, in alternative hypothesis, you will write, no, this population or this group of people are representative of the entire population. Then you perform your statistical inferences based on the data that you have, and you make the conclusions thereon. It's called the null hypothesis or the default hypothesis because we tend to measure it towards zero or negative things. So that's why it's called null hypothesis. On the other hand, alternative hypothesis is trying to prove something in a positive direction. So that's why it's called alternative hypothesis. Now, in the next question, we're trying to understand when you are creating a statistical model, how do you prevent overfitting? Overfitting is by far one of the most common issues that comes with statistical modeling. This is the kind of problem that you get when you have some training data and some testing data. You create a statistical model using the training data, and in the training data, when you again try to make the predictions, you get 100% prediction. On the other hand, in the testing data, when you try to pour in the data and get the responses, you get really varied result. The accuracy is really low, around 50%, 40%. So when you're creating a statistical model, you get this overfitting problem when the data set that you use for training leads to a good performance when you use it on the model, but on the testing set, it is very poorly performing. This is because the statistical model essentially analyzes and then remembers everything about the training data. So when it's being trained, it takes a look at all the values and it draws the conclusion that, okay, I have remembered everything. Now when these values come, and I will be able to answer it perfectly. But if, for instance, a new value comes in that the model hasn't seen, it will have no idea and will just try to guess it, and it will get it wrong most of the time. That's what overfitting means. How do you prevent overfitting? You do it by cross-validation. Cross-validation basically means you get the data set that you want to train your data on, put it in 10 different groups. So basically divide the data set into 10 parts. Then generate the model and use 9 parts for training and 1 part for testing. That 1 part, you are going to alternatively pick all the 10 parts one by one and let all the other 9 parts be for training purposes. That's how you can do it by cross-validation. Then comes skewed distributions. In case you're not familiar with skewed distributions or distributions in general, distributions basically mean how do you plot a data and how the frequency of the data is determined here. Now, there are two kinds of skewed distributions, left skewed and right skewed distributions. So what is left skewed distribution? A left skewed distribution is one where the left tail is longer than the right tail. So it is important to note that in a skewed distribution, mean is smaller than median and median is smaller than mode. For those of you who don't understand what mode is the value that is occurring most frequently. If I have 5 values and they are 1, 2, 4, 5, 5. 5 is the mode of the values because it occurs most number of times. Now, when we take a look at left skewed distribution, it is different from symmetric or normal distribution. In normal distribution, mean is equal to the mode and the distribution is completely symmetrical. It's same on the left hand side than it is on the right hand side. In left skewed distribution, however, the tail is longer than that of the right tail. So on the left hand side, there's a longer tail to the distribution than there is on the right hand side. It is important to note that the mean is smaller than median and median is smaller than mode, other than the ones that we take look at in normal distribution in which mean was equal to the median. Here the mean is smaller than the median. Then comes what is right skewed distribution. So similarly to left skewed distribution, right skewed is the diametric opposite of that. You get a right skewed distribution when the right tail is longer than the left one. So if the right tail is longer, left tail is shorter, then you get mean that is larger than the median and median that is larger than the mode. So hopefully that makes it clear. In normal distribution, mean is equal to the median. In left skewed distribution, mean is smaller than mode. And in right skewed distribution, mean is larger than median. So that's how this works. Mean and median, the relationship between mean and median can be used to describe what kind of a distribution we'll get if we plot the entire data set. So if you have calculated the mean and median, instead of plotting the entire data set, you can simply take a look at and compare the mean and median to figure out what kind of a distribution will it provide you with. You can also calculate the mode. However, mean and median tend to have the largest effect on these data sets. So here's a question that gets asked very frequently. The values might change, but it gives you a good understanding of how you can use the quantities in your understanding of a hypothesis. If a distribution is skewed to the right and the median is 20, what will be the mean of the data? Will it be greater or less than 20? So basically the question is the mean greater than the median or is it less than the median in a right skewed distribution? Since we saw it just now, if the given distribution is right skewed, then the mean should be greater than 20, while the mode remains to be less than 20. So that's how it's supposed to work. Mean is the greatest, then there's median, which is smaller than the mean, which is 20. Median is 20, mean is supposed to be greater than that. How great, it doesn't really matter. And mode is the smallest value in this entire equation. So that's how the right skewed distribution works. Then comes what are the kinds of biases then you can encounter while sampling. For those of you who are unaware, sampling is the technique that you use in order to extract some small sample out of a large population of data. So different kinds of sampling are available. In medical field, they use different kinds of sampling than in statistical fields. One way to sample is, let's say that you are trying to collect some data about medical patients. So you can take a look at every third patient that comes in and you use that third patient's data. So now your data set that you have will be reduced by a third. So instead of if 100 patients or 33 patients come into your clinic every day, you only have data about 11 people. So now you have only 11 people. They are selected randomly. Whoever comes first, second, or third, you don't change the order. You just keep the order and pick the third person. So that's how you can do this. Now, there are certain biases. Biases are basically errors in sampling. When you're sampling something, you end up choosing one over the other, and that leads to some error. So what are the three kinds of major biases that you could have? These are selection biases, survivorship biases, and undercoverage biases. These are all important biases, and we'll take a look at those one by one. But it's important to understand that these biases heavily affect the information that we get, and if we get wrong information, we're going to draw the wrong conclusions about the entire world, about the entire population of the data that we have. So let's take a look at selection bias first. This is an important question. Usually people start by asking the different kinds of biases and then they go one by one. If you are confident enough and you answer one of the biases with a good level of confidence and understanding and good wordings, they might not ask you about different kinds of biases because they know that you know what you're talking about. But in case you don't, they still ask you. So what is selection bias? Selection bias is a kind of error that occurs when a researcher decides who is going to be studied. So basically, selection bias occurs when a researcher who's supposed to research the entire data set gets to make the decision about what are the people who are going to get studied. This is not done randomly. This is done on the basis of preconceived notions by a particular researcher, and that could lead to really difficult problems. So in order to say that, let's say that you are trying to study the population of an entire city, and what you do is you just say, okay, give me the top 10 earning people of the entire city. Now the population is not going to be represented by the sample. You only get the top 10 most highly paid individuals. You might not get everyone, and your study might be really off to what the conclusion should be. Now it could be possible that the conclusion that is drawn could be correct, but you will never know unless your sampling technique was correct. So that's a selection bias. Then comes survivorship bias. Survivorship bias draws its name from the word survivor. That's the key word here. Survivorship bias is the flaw of the sampling technique, sampling selection technique, that occurs when a dataset is only considering the surviving or existing observations and fails to consider the observations that already ceased to exist. If you're trying to study about certain species of fishes, make some conclusion, then the fish and the species that have disappeared throughout the history of living creatures, those species are not considered, then your results might be a bit off. So that's survivorship bias. You can take a look at other nuclear disasters or man-made disasters in which people died, and if their data is not considered, then you might not get an accurate picture of what the data set that you're trying to get is. So that's survivorship bias. And then comes undercoverage bias. So undercoverage bias is a bias that occurs only when some members of the population are inadequately representative or undercovered in a sample.
Okay guys, if you're looking for an end-to-end training in statistics, Intellipaat provides a complete certification training on statistics for data science, and those details are available in the description box below. Now let's continue this session.
So let's say that you are trying to predict you're trying to make a prediction about certain people. The population contains 30% of the people in the population are below the age of 18. The rest out of the 30%, if you remove the 30%, out of the 70%, 60% are above the age of 18 but below the age of 40, and rest 10% are above the age of 40. So that's how you get it. You get 30% less than 18, 40% out of the 70% to be, or let's say like 60% out of the 70% to will be between the ages of 18 to 40, and 10% above the age of 40. Now, when you're trying to create a sample, let's say out of those 100 people, you're only trying to get 10 people, then you need to be able to take into account all of this and create as close to possible the real world situations as you can. So, and you pick many ways of doing this. One of the ways is you take a look at the different categories, take a look at the distribution throughout the population, and then you choose that many people. So since there are 30% people below the age of 18 in our population of 100 people, we take 3 below the age of under 18 people through the population. Therefore, our sample. For the next, we have 60% of the people between the age of 18 and 40. So we take 6 people out of that age group in the population. And finally, we take 1% above the age of 40. So we have an accurate representation of the entire population. If we don't do this, then we get a bias in our entire research, and that bias is called undercoverage bias. This is really important to be understood, because if the bias is giving us the undercoverage bias, then our data set is not representative of the population, and we get a lot of errors throughout the entire thing. So we need to be able to cover for that undercoverage bias and understand if it has occurred. If it does occur, then we need to understand how to use it in a better way. Then comes skewness. So this is a question, as we have already taken a look at what is right skewed and left skewed. The question here is, what is skewness? So it is important to be able to describe what skewness actually is. Skewness is a measure of a lack of symmetry in data distribution. If you want to take a look at how skewness works, basically you have symmetrical distributions, and if it's not symmetrical, then it's either skewed on the left or on the right. These are the only 3 options that you have. So that's what skewness is all about. It's about a lack of symmetry in the distribution of the data that we have. Then comes kurtosis. This is a concept that not a lot of people take a look at. It's a scary sounding word, but it's actually quite easy to understand once you wrap your head around the entire idea of skewness and kurtosis. But kurtosis is basically used to describe the extreme values in one versus the other tail. It is actually a measure of outliers present in the distribution. So if you have an entire population and you have values on the extreme end of one point, so there are values that are below the necessary values in the first quartile and above the necessary values of third quartile. So you have outliers on both the extreme ends. Then there's a high kurtosis. Kurtosis is used to describe the extreme values in one versus the other tail. So what are the values that are on one side of the number line, and values on the other side of the number line, going in the positive direction and in negative direction. How many outliers are there? What are the kinds of outliers that are present? And that's the kind of thing that kurtosis allows us to figure out. Then comes correlation. Now, correlation is used to test the relationship between quantitative variables or categorical variables. They sound very much similar to covariance. The important distinction between correlation and covariance is that correlation is used to measure the magnitude of the relationship. So correlation usually ranks from -1 to +1. So the value of a correlation between two variables is going to be from -1 to +1. -1 being an extremely negative correlation, +1 being the extreme positive correlation, and 0 means there is no correlation. Now, what that means is in covariance, we try to figure out whether or not the relationship is proportional or inversely proportional. That is, a value increase in one variable is going to lead to the increase in value in another variable, or is it going to lead to the decrease in value of another variable? On the other hand, in correlation, what we get is we get to get the magnitude of the covariance. So to give you an example, how much will a particular variable change in one variable lead to a change in another variable? Whether it's positive or negative, that's a different thing, but how much is it going to be? So if it's 1, then it's going to be increasing as much as the positive value increases. So to give you an example, if I have 7 as a value, I increase it, the other value that has 3 will also increase by 1 or 2, whatever. So that's the thing that we're trying to get across. It's the magnitude of how strongly these values are correlated that determines whether or not change in one value is going to lead to change in another value, and how much is it going to be. So now no one usually gets 0 correlation. Each value is due to some inferences and noise in the data get some sort of correlation between two variables. But in order to regard these two correlated variables, what we do is we take a look at the correlation and we try to figure out what could be causing that correlation instead of focusing on the little details. So if you have two variables that are correlated by the degree of 0.2, 0.3, then it's not significant and you don't need to worry about it. If it's above 0.5, let's say 0.6, 7, 8, 9, or 1, or below 0, negative 0.5, negative 0.6, 7, 8, 9, 10, then that means that you are running into an error, and a lot of correlation of variables are strongly correlated, then you need to drop one of the correlated variables. So you just need to understand that. Finally, we have the relationship between standard deviation and standard variance. These two things sound very similar, but they have really different measures. So standard deviation is the square root of standard variance. This question can also be asked in a reverse format, which is how does standard variance relate to standard deviation? The answer would be it is standard deviation squared. Standard variance is the standard deviation squared. So you multiply standard deviation value by itself and you get standard variance. These are just used to determine how the values work and how do you use them. This question is asked mainly because people get confused between standard deviation and standard variance, and that could lead to a lot of confusing issues. So these are the kinds of things that you should understand when you're trying to learn these technologies and learn these terminologies, because the problem here is that deviation and variance are quite closely related. But how do they relate with each other? Which value is the square root of which value is going to be the deciding factor of whether or not you're right or wrong. With that, we have come to the end of all the questions that we had.
Okay guys, if you're looking for an end-to-end training in statistics, Intellipaat provides a complete certification training on statistics for data science, and those details are available in the description box below. Okay guys, that's it for this session. I hope this session was helpful and informative for you. If you have any queries, leave a comment down below. Or if you have any new suggestions for us to make as a video, please leave that also in the comment section down below. So thank you, meet you in another session.